Welcome back to this channel. So in this video, we are going to be introducing solubility equilibria. So solubility equilibria is going to be divided into two videos. One is going to be this video and specifically introducing and giving explanatory notes about solubility equilibria and solubility as well. So this video is presented to you by Ogembe Yusuf. I advise you subscribe to the channel and share the video to your friends, so that you can all benefit as a family. Solubility equilibria, we are going to first start by defining what solubility is before we start on solubility equilibria and solubility calculations. So looking at solubility, the definition of solubility, as we defined it at O level, is going to remain the same definition, except there are going to be some conditions that are added. So solubility is going to be the maximum mass of a solid, but this mass must be in grams, that can circulate 100 grams of a solvent at a particular temperature. And this is the condition. When you're defining something under equilibrium, make sure that you include the condition. So mass of a solid in grams that can circulate 100 grams of a solvent at a particular temperature, but it's done in presence of excess or undissolved solids. Now the units for solubility, or after calculating solubility, are going to be grams per 100 grams of a solvent. Or simply, you can write it in short form or in terms of formula by saying grams, and then in brackets you put 100 grams of a solvent per -1 or per solvent. So let's look at the molar solubility. So solubility is different from the molar solubility in that here we are going to be looking at moles. So we're going to define molar solubility as the number of moles of a solid that can circulate 1 liter of a solution before the solution becomes saturated. So number of moles of a solid that can dissolve in 1 liter of a solution before the solution becomes saturated is going to be called molar solubility. And then the units for molar solubility are going to be moles per liter, or it can be denoted as capital M. Experiment to determine the solubility of any soluble salt. For example, if you are to consider potassium nitrate. So first of all, we are going to add potassium nitrate liter at a time while stirring to a known volume of water, which is going to be immersed in a container and then placed in a thermostat, and this is done to keep the temperature of our apparatus constant until normal nitrate or normal potassium nitrate dissolves. Now the mixture is going to be allowed to settle until the excess undissolved crystals of potassium nitrate separate from the solution, and then the excess undissolved crystals are going to be filtered off using a dry filter paper, which you do in the laboratory, and then a funnel, because they're the ones that are used in filtration, and they're going to be filtered off into a dry container so that we can obtain only the saturated solution of potassium nitrate. Now here, the temperature of the saturated solution is going to be measured and it's going to be recorded as T degrees Celsius. Remember that this is going to be the temperature of the saturated solution that you filtered out. Now a clean dry dish is weighed and its mass is recorded too, and this mass we are going to say that it's going to be a grams. And then a known volume of the saturated solution is going to be added to the dish, and the dish and the saturated solution are also weighed together again, and the mass is recorded as big grams. Now the dish and the saturated solution is going to be placed on a steam bath until the dry potassium nitrate crystals are left. The dish and the saturated solution are going to be placed on this steam bath, and the steam bath is to evaporate off water so that the saturated solution can form back the crystals that we dissolved in it again. So it put it on a steam bath until the dry potassium nitrate crystals are left on the dish, and therefore we allow the dish and its contents to cool, and therefore weigh the mass of the dish and the dry salt to be 6 grams. of results, our mass of the dish, we say that it's going to be a grams. Mass of the dish together with the saturated solution is going to be b grams, and then mass of the dish and dry potassium nitrate is going to be 6 grams. Now mass of temperature of our saturated solution, we say it's going to be 10 degrees Celsius, and then the mass of the saturated solution, to get mass of the saturated solution, we are going to get mass of the dish and the saturated solution together, and then we less the mass of the dish, so that we can remain with the mass of the saturated solution, which we want. So mass of the saturated solution is going to be got by B less A, which is in terms of grams. And then mass of the dry potassium nitrate, mass of dry potassium nitrate is going to be got by getting the mass of the dish together with dry potassium nitrate, we less the mass of the dish, so that you can only remain with the mass of dry potassium nitrate. So it's going to be C minus A. Now mass of water, remember that these ones are all, this was a saturated solution was got by getting water, a non-volume of water, and then dissolving dry potassium nitrate crystals. So for us to get the mass of water, that means that we have to get the mass of the saturated solution with less the mass of the potassium nitrate. Because to get the saturated solution, we mix dry potassium nitrate and water, and therefore to get the mass of water that we used, we get the mass of the saturated solution, we less the mass of the dry potassium nitrate crystals, so that we can get the mass of water, which is going to be B minus C grams. So we are going to be saying B minus C, or the mass of water dissolved C minus A. C minus A refers to the mass of the dry potassium nitrate, which is present here, as I explained how we got it. So mass of water, this mass of water dissolved this mass of potassium nitrate at a specific temperature at 10 degrees Celsius. Then what about 100 grams of water? Because that's how we measure solubility. So 100 grams of water are going to dissolve mass of dry potassium nitrate crystals divided by mass of water used times 100 grams of a solvent, which was our water, in terms of grams of potassium nitrate at the same temperature. And therefore, since this is mass in 100 grams of a solvent, which is water, this expression qualifies to be our solubility, and that's how we calculate for solubility. So you're going to be saying that, therefore the solubility of potassium nitrate is going to be this: grams per 1,000 grams of water at 10 degrees Celsius. Always remember that the solvent that you are going to most commonly use here is going to be water. So let's look at the factors that can affect solubility of a soluble salt. So first of all, we look at the nature of the solvent and the solid. The other one is going to be temperature. Remember that always increase in temperature increases solubility, as well as pressure. Increase in pressure is also going to increase solubility of any given solid. Examples that you can be using so that you can calculate for solubility in any given question that may be presented. Now mostly these questions, in case they are asked, they are brought in paper 1. So part A, we are having that 350 centimeters cubed of water was saturated by 157.5 grams of potassium nitrate, and this was done at a constant temperature of 30 degrees Celsius. Now we are prompted to calculate for the solubility of potassium nitrate at the same temperature. Now the density of water is going to be 1 grams per centimeters cubed. And part B, the solution in A was cooled to 15 degrees Celsius. Now calculate the mass. Now here they are trying to show you the effect of temperature. And we say that increase in temperature increases solubility, and decrease in temperature is going to decrease solubility. They are directly proportional. So here we are supposed to calculate for the mass of potassium nitrate that is crystallized. If we are told the solubility of potassium nitrate at the same temperature is going to be 25 grams per 100 grams of a solvent. So part A, we are going to start by calculating for the mass of water. So mass of water is going to be got by 350 times 1. Now we are doing this because we are given volume. Volume was 350, and the density of water is 1 grams per centimeters cubed. For us to get mass, we get volume times density. So 350 times 1, which is the density of water, we get 350 grams. now that you have the mass of water used. So this mass dissolved the given mass of potassium nitrate. Then what about 100? Because that's how we calculate for solubility. So you're going to say that 350 grams of water were saturated or are saturated by 157.5 grams of potassium nitrate. And this is done at 30 degrees Celsius or at a constant temperature. Then what about 100 grams of water? Because that's what solubility is. It must be in 100 grams of a solvent. So 100 grams of water are going to be saturated by 100 times 157.5 divided by 350 grams of potassium nitrate. And this is done at 30 degrees Celsius, which is going to give us an overall mass of 45 grams per 100 grams of a solvent, which was our water. And therefore, that's our solubility since it's in 100 grams of our solvent. So you're going to conclude and say solubility of potassium nitrate is going to be 45 grams per 100 grams of water at 30 degrees Celsius. So going to part B, where we lowered our temperature from 30 to 15, they already gave us the solubility which was involved. So we are going to start with that statement. 100 grams of water are saturated by 25 grams of potassium nitrate at that temperature. Then what about the mass that they talked about, or the mass that we are given? Now this was a typing error about 300 grams of water. It would have been 350 because it's the volume that we used. So you change this when you're taking your notes. What about 350? That means that the answer also here is going to be altered. So 350 grams of water which we used, which is the volume of water we used, is going to be saturated by 350, not 300, times 25 divided by 100. Also the answer is going to change. Grams of potassium nitrate. Now after getting this answer, this is the mass that was saturated by the volume of water we used. Remember that we converted volume into mass by this expression that we did in part A, the first expression. So mass of potassium nitrate formed by cooling of the solution from 30 to 15, you are going to get the mass, the initial mass that was present or that was saturated by 350 grams, which was this one up here. You bring it here and you also less that one that is saturated by the same mass. You less that one that is saturated by the same mass by getting a different answer because you have altered the value here. So it's going to be 350 times 25 divided by 100. The answer you get is what you subtract from this, which is going to be around 80 something. And therefore you're going to be having a varying answer, but that's how you're going to calculate for the mass of potassium nitrate formed after cooling the solution from 30 to 15 degrees Celsius. Part B, 60 grams of a saturated solution of a soluble salt CHU gave 17.75 grams of CHU at 50 degrees Celsius. Now we are required to calculate for the solubility of CHU at the same temperature. Now we are supposed to first get mass of water, and we are going to get mass of water since we have 60 grams of a saturated solution and we have the mass of the solid. The saturated solution I told you is good by getting the dry solid and dissolving it in water. So we can get the mass of water from by getting mass of the saturated solution with less mass of the salt, so that you can remain with the mass of water that was used in the experiment. So the mass of water which was used in the experiment is 42.25, and it's the one which saturated the mass, or which saturated the mass of the dry solid given, which is 17.75. So 42.25 grams of water are saturated by 17.75 grams of our dry solid CHU at a specific temperature. Then what about 100? Because solubility is measured in terms of 100 grams of a solvent. So 100 grams of water are going to be saturated by 100 multiplied by 17.75, then divided by 42.25 grams of CHU, and this is done at the same temperature, and you're going to end up with the solubility being 42 grams per 100 grams, which is the units of solubility, and therefore you're going to conclude that solubility of CHU is going to be 42 grams per 100 grams of water, which is done at a specific temperature or at the same temperature which you are conducting an experiment on, or 50 degrees Celsius. So part C, we are going to say that the solubility of potassium chlorate is going to be 60 grams per 100 grams of water. I remember that I told you whenever I see per 100 grams of water, that those are units of solubility. That means that I have given you solubility. And it's the statement that you have to first start with and reverse it. And this is done at a specific temperature of 100 degrees Celsius. Now we are being told to calculate for the number of moles of the solid that can circulate 100 grams of water at the same temperature. Now we have to calculate for the mass of the solid that was dissolved by this 150 grams. Since we have solubility, we are going to say that 100 contains 60. Then what about the mass that we used, which is 150? So 100 grams of water are saturated by 60 grams of potassium chlorate at the same temperature. What about 150 grams that we used of water are going to be saturated by which mass of our salt? And we are going to have 150 multiplied by 60 divided by 100, ending up with 90 grams of potassium chlorate. Now we have to convert these 90 grams into moles, like we have been doing. When you have been given mass and you want to convert it to moles, that means that you have to calculate for the molar mass. And once it is molar mass, you give it units. If it's relative, you don't give it units. So molar mass of potassium chlorate is going to be 39 because we have one atom of potassium, and then plus 35.5 because we have one atom of chlorine, plus 3 times 16 because we had 3 atoms of oxygen, which are going to give you 48. And adding everything in the calculator, you're going to end up with a total mass or total molar mass as 122.5 grams. Now we are saying that here, moles of potassium chlorate are going to be equal to given mass divided by the molar mass. And your answer in the calculator is going to be 0.735 moles. And these are the moles of the salt that can circulate 150 grams of water at the same temperature. Aspects which are going to be involving solubility products. Now most of the video, most of solubility equilibria is going to be full of solubility products. I advise you to understand the basics of the theory. In this, we are going to be looking at all the theory and all the explanation questions, or all the examinable explanations that can be set under solubility equilibria. So under this topic, we are going to be considering only sparingly soluble salts. That means that salts which are not soluble in water, but we assume that when they're in water, their ions separate, but they are assumed to be sparingly soluble. So since they are sparingly soluble, part of the compound which is sparingly soluble dissolves, but most of it is left undissolved. So we assume that it makes a saturated solution, and that saturated solution that it makes, it gives us cations or anions that are present in that particular compound. So here we are going to be considering soluble electrolyte AXBY, and we are saying that here the ions of the electrolyte in its saturated solution are going to be in equilibrium with the undissolved solid at a given temperature. And you have represented it by this equation. So here, notice that all the equations you are going to be making must have a reversible arrow. And for you to write any equation, you must say plus the aqueous part to show that you are converting this solid into the aqueous ions. Like I've explained to you, part of it dissolves, but most of it does not dissolve. That's why we call this topic solubility equilibria. So we expect the solution formed after trying to dissolve it, and most of it does not dissolve. We expect the solution in which it is in to be saturated. So from the law of mass action, which looked at in chemical equilibria, solubility product, OK, or the ionization constant or dissociation constant is going to be equal to molar concentration of your products raised to their appropriate powers, and their appropriate powers are going to be their stoichiometric coefficients. Is what you call the appropriate powers. They are their stoichiometric coefficients. Another product is Bx. Its stoichiometric coefficient is Y. Then divided by the molar concentration of our product, which is this. But notice that here I told you that most of these salts are sparingly soluble. So we consider that the product is going to be dissolved, the concentration at which the product is dissolved is going to be very minor. So it's going to be, its concentration is going to be assumed to be left constant at the beginning and the end of the experiment. So that's why we consider the O of this concentration of our product to be 1, and therefore we do not consider the concentration of the solid or our reactant. So you're saying that here, since concentration of the solid remains constant, then I mean we approximate it to 1. That means that you're only going to consider product of the molar concentration of our products raised to their appropriate powers at a specific temperature. So solubility product, which is denoted by capital K and then subscript SP, is going to be equal to molar concentration of our products raised to their appropriate powers, or someone can say raised to their stoichiometric coefficients at a given temperature. And solubility product is going to be denoted by capital K and then a subscript of SP. So you're saying that here, constant KSP is going to be called the solubility product of a sparingly soluble electrolyte, which is AXBY, as we gave it in the example. Now let's look at the definition of solubility equilibria according to the expression we just derived. So here we are going to be saying that here, solubility equilibria is therefore going to be defined as the product of the molar concentrations of the ions of a sparingly soluble electrolyte that are present in a saturated solution raised to their appropriate powers. But this product of this concentration of the ions of a sparingly soluble electrolyte must be at a given temperature. Just like I told you, every definition you define in equilibria must contain a condition, and always that condition is always going to be a given temperature. So solubility equilibria is therefore going to be defined. You must know this definition because almost every question that you are going to come across that involves solubility equilibria, we are going to be asking you for the definition of this term. So you must know the key elements. First of all, we cannot give you a mark without a condition. The condition is very important. So at a given temperature is what is going to qualify whether you get a mark or not. And then the underlined words is where the marking point is going to be given. So you find that the whole definition is going to carry a minimum of 1.5 a mark according to the marking points that are present. So solubility equilibria is going to be the product of the molar concentration of the ions. Molar concentration of the ions, but these ions are of a sparingly soluble electrolyte, which are present in a saturated solution, and they are going to be raised to their appropriate powers, provided it is at a constant or at a particular or at a given temperature. Let's look at the expressions that are going to be involved in solubility equilibria. Now, like I said, solubility equilibria, you're going to be considering salts that are sparingly soluble. So you're going to be considering sparingly soluble electrolytes such as the ones mentioned below. And for each equation that is involved in solubility equilibria in water, the solubility product expression is going to be written for each of them. So first of all, silver bromide is a sparingly soluble salt. We are going to be looking at how its solubility equilibria equation can be got. We also look at the solubility equation for silver ethane dioate. We also look for the equation of the solubility product of calcium phosphate. So first of all, like I said, you get a sparingly soluble salt, which is silver bromide. You add aqueous to show that you are dissolving to get the ions that are present in its saturated solution at a given temperature. So when you dissolve this in aqueous or in its saturated solution, we are going to have its ions to be silver ions, which are present in aqueous, and then bromide ions, which are also present in aqueous. But I told you, remember, that you are always going to be using reversible arrows. So going to silver ethane dioate, dissolving it in aqueous solution, we are going to have ions of silver and then ions of oxalate or ethane dioate ions. And you are using a reversible arrow to show that it's going to be a solubility equilibria equation. Now for solubility equilibria equations, the expression is denoted by KSP. I told you ignore the concentration of the product because its concentration is assumed to remain the same at the beginning and the end of the experiment. So that means that its concentration is not altered. So we assume it's 1. That's why we only consider molar concentration of the ions which are present in its saturated solution, raised to the appropriate powers. Now the appropriate powers they are raised to must be coefficients which are put here. So here you are seeing that is 1, 1. That's why these brackets, the molar concentration brackets of the ions are not raised to any power because the powers are 1 to 1, which is going to remain constant. But if you look at silver ethane dioate, if you ionize this, you're going to find that to balance the equation now, first of all, you balance the charges. If you can't balance the charges, you balance the atoms. So writing the equation, we separate it into silver ions. So balancing the atoms, we're having silver 2 here. That's why I put here 2 to make the silver atoms 2. And then the oxalate ions, or ethane dioate ions, they are 1, so we make it 1. So charges are balanced, that means the equation is balanced. And you have used reversible arrows to show that we're handling a sparingly soluble salt. So the expression for the sparingly soluble salt, which is denoted as KSP, is going to be equal to molar concentration of our ions. In this case, it's going to be silver ions, raised to the appropriate power. The appropriate power which is present on the silver ions is 2. If you look here, that's why this molar concentration bracket is raised to power 2. Then times the molar concentration of the oxalate ions. Now oxalate ions, since the coefficient is 1, the appropriate power is going to be 1, and the expression remains the same. So looking at the expression for calcium phosphate, dissolving it in water to see the ions it's going to give after being sparingly soluble, using reversible arrows, it's going to be 3 calcium ions since we're having 3 calcium atoms this side, and then plus 2 phosphate ions since we're having 2 phosphate ions this side. So after balancing up the atoms, you ensure that charges are balanced, and then you write your expression for solubility equilibria. Like I said, expression for solubility equilibria is capital K and then a subscript of SP. So molar concentration of the calcium ion raised to the appropriate power, which is going to be 3, because 3 is the stoichiometric coefficient present in the equation. We consider them as appropriate powers in the definition. So times the molar concentration of your phosphate ions raised to power 2. 2 is your stoichiometric coefficient. Look at the conditions that are going to be involved under which solubility equilibria is going to be valid. So solubility equilibria is only going to be valid if at all the temperature is kept constant, and also if the solution in which our sparingly soluble salt is going to be saturated. And the other thing is that the electrolyte used, or the salt that you are using for this experiment, must be sparingly soluble. So always remember these conditions. Temperature must be kept constant, the solution must be saturated, and then the electrolyte must be sparingly soluble. Now let's look at the experimental determination of our solubility product. So solubility product of different sparingly soluble electrolytes can be defined by any of the following methods. Now usually when you're asking you for these methods, we examine them in paper 1, and we ask you, other than the method used to calculate for the above KSP, find any two, or name or identify any other 2 methods that can be used to determine solubility product of such a compound. So you must be knowing the different methods by which we use to determine solubility products. So one of them is going to be direct titration, and then the other one is going to be using conductivity measurements, and then the other one is going to be using electrode potentials. So you should know all of them, but here we're only going to look at a few. We are going to look at direct titration and use of conductivity measurements as the 2 described experiments. So here we are going to the first 2 methods will be used in this topic, but more about conductivity measurements and electrode potentials will be seen in the topic of electrochemistry, as we shall be covering it on this channel. So however, for examination purposes, any method can be used, because the examination is not going to tell you to be specific at any method. They'll just tell you to describe. They'll just tell you to describe an experiment to determine solubility product of any compound that they will give you. So it's your prerogative to choose whether you are going to go with direct titration or conductivity measurements. You try to be positive on all the 2 procedures or methods and see the one which is easier to remember so that you can go with that one. So let's look at the experiment that can be used to determine solubility product of calcium hydroxide. Now notice that for direct titration, we involved acid to base titrations. So it requires bases, but for conductivity measurements, for it is non-selective. So this one is even better to go with as compared to direct titration. The titration method. Now using titration, we are going to have, remember that we are dealing with sparingly soluble salt. So we expect you to be dealing with a solid, dissolving it in water. But that solid must be sparingly soluble. That means that you must shake the bottle, but it should not dissolve. So that's the steps in which you are supposed to describe your experiment. So Roman number 1, or the first procedure, we are going to get excess solid calcium hydroxide and we are going to add it to a given volume of distilled water, which is present in a container. And then we are going to close that container and then we shake the mixture vigorously for some period of time, and then we leave it to stand at a constant temperature. And the reason why we are leaving it to stand at a constant temperature is because we want equilibrium to be attained. Now after equilibrium being attained, we get the mixture and then we filter it. And we do this so as to obtain the saturated solution of calcium hydroxide present as a filtrate. We want the solution because remember the ions that we are getting must be in terms of the solution. We cannot get them from the salt that did not dissolve. As we shake this solid in this known volume of water, part of it dissolves, but majority of it does not dissolve. So we are interested in the saturated solution that contains the ions that dissolved partially. So that's why we do the filtering so that we can attain our saturated solution containing the ions present in calcium hydroxide, and that's going to be calcium ions and then hydroxide ions. Now we need the molar concentration of the respective ions. So what we do is that we do what we call titration. So a known volume of the filtrate is going to be pipetted and it's going to be put into a conical flask and it's going to be titrated. Remember that we are dealing with calcium hydroxide. That means that the titrant must be an acid. So it's going to be titrated with a standard solution of hydrochloric acid. And whenever we use hydrochloric acid, we accompany it with methyl orange indicator. So having calcium hydroxide in aqueous, because it's infiltrate, reacts with hydrochloric acid, which is standard, to get us calcium chloride and water. Now we use the known volume of hydrochloric acid that we got to determine the molar concentration of calcium hydroxide solution. So that's why here we just say that here the molar concentration of calcium hydroxide solution is calculated using the equation above because our HCl was standard. And after getting molar concentration of calcium hydroxide, first of all, by taking molar concentration of calcium hydroxide to be x moles per liter, assuming that you got it as x moles per liter, we write the equation for the solubility product of calcium hydroxide. Just like others, you also put here plus aqueous. Remember that this one must be reversible arrows. So the ions you get from calcium hydroxide are going to be calcium ions and then plus 2 hydroxide ions. So I put here 2, first of all to balance the charges and also to balance the atoms. So after ensuring that charges are balanced and the equation is being balanced, then you can use mole ratio. This is the only equation or the only topic whereby we use mole ratios to calculate for the molar concentration of the ions. It's the only topic whereby a reversible reaction can be used to calculate for the molar concentration or moles of the ions present in the solution. So we use mole ratio to determine the molar concentration of our ions, because remember that we are not interested in the molar concentration of calcium hydroxide. So you're saying that here, since the mole ratio of calcium hydroxide to calcium ions is 1:1, that means that the molar concentration of calcium hydroxide present is going to be the same as the molar concentration of the calcium ions present. But remember that you had already got the molar concentration of calcium hydroxide to be x moles per decimeter cubed, which is the same as the molar concentration of calcium ions. Now here, if you had to consider mole ratio, you are going to see that mole ratio of calcium hydroxide to the hydroxide ion is going to be 1:2. So here we are saying that here, since mole ratio of calcium hydroxide to the hydroxide is 1:2, That means that molar concentration of the hydroxide ions is going to be twice the molar concentration of calcium hydroxide present, and therefore we are going to have it as 2x moles per decimeters cubed. Now after doing that, we'll write the expression that can be used to calculate for the solubility product of calcium hydroxide, and that's going to be from this equation. So the molar concentration of our molar concentration product of the molar concentration of our ions, which is calcium and hydroxide. Calcium is raised to power 1 because it does not have any coefficient from the equation, and hydroxide concentration is raised to power 2 because it has a stoichiometric coefficient of 2 in the equation. And then since we have already got the molar concentrations of these ions, we substitute them, and this is going to be x times molar concentration of the hydroxide is 2x, and then you put it in bracket squared. Now opening this bracket, this is going to be 4x squared. Now 4x squared times this x is going to give us 4x cubed as the formula for calculating KSP, or the solubility product of calcium hydroxide present at a particular temperature. And the units are going to be depending on how you are using your definition, or the powers present on your formula used to calculate for the molar, used to calculate for KSP. So since it's cubed, we assume that for us to get that formula, it was moles per decimeters cubed. But it must be, but this moles per decimeters cubed here was cubed. So using the laws of indices, this 3 comes here so that you can end up with mole power 3. And then 3 times 3, you end up with dm power negative 9. And that's how the formula for calculating KSP, or the experiment for calculating KSP of calcium hydroxide is conducted. By another method, and this method you are going to be using conductivity measurements. So when you're using conductivity measurements, this is the same as formula whereby you are going to be using electrochemistry knowledge. Now if you are serious with this topic, I advise you to focus more on this method because this method is non-selective and it can be used on each and every sparingly soluble salt. And this method is also going to help you to properly master your electrochemistry. So this method is the most appropriate one for someone who is very serious at chemistry. Now formulas, or the units which have been put in brackets are not a must for you to write them. You can just write K of the solution and K of the water. Now let's start. We are saying that here we are going to get our excess calcium hydroxide and we add it to a given volume of solid water in a container. And we are going to close this container and then we shake the mixture vigorously. And we do this for some time, for about 5 minutes, so that we can get the dissolution. Remember that we are dealing with sparingly soluble salts, so it's very hard for them to dissolve. That's why we shake them for a given amount of time. And after shaking them, we leave the apparatus to stand at a given temperature. And this is done so as to attain equilibrium. Now the mixture is thus going to be filtered later so that we obtain the saturated solution of calcium hydroxide as the filtrate, just like I explained earlier. Now what varies this experiment from the previous method is going to be this. So after getting your filtrate, here we get the electrolytic conductivity of the standard solution. So electrolytic conductivity of the standard solution is going to be denoted by K solution. So this K is denoting electrolytic conductivity, and then solution showing that electrolytic conductivity of the solution is going to be measured using a conductivity meter. I told you that you can either include units or you can leave them out. It's not a must. You get your marks. And then the electrolytic conductivity of water, which is going to be denoted by K and then the symbol of water down to give us the electrolytic conductivity of water at the same temperature, is also going to be obtained. But here is not going to be obtained from our solution. It's going to be obtained from books or from history. Or someone can just say electrolytic conductivity of water is already known. And then there we are going to proceed by saying also the molar conductivities at infinite dilution, which is going to be denoted by this. Molar conductivity at infinite dilution of the calcium ions and the hydroxide ions are going to be obtained from tables. So we are going to, after that, we treat our results. So we are going to be saying that electric conductivity of our calcium hydroxide is going to be obtained by, now here when you're in electrochemistry, we tell you that electric conductivity of a solid is equal to electric conductivity of a solution less electric conductivity of a solvent. But here now we specify them that electric conductivity of a solid here is now going to be calcium hydroxide. So electric conductivity of calcium hydroxide is going to be equal to the electric conductivity of our solution less electric conductivity of our solvent, which is water. And that's the expression that's going to enable you get the electric conductivity of calcium hydroxide. Now the molar conductivity of calcium hydroxide present at infinite dilution is going to be obtained by the following, and you are going to be looking at this furthermore in electrochemistry. So if you want to magnify your knowledge, you'll be waiting for electrochemistry video explanations. If you're in senior 6, I hope you have already covered it yet, so you should be well conversant with this. So the molar conductivity of calcium hydroxide at infinite dilution is going to be obtained by the following, and this is done according to Corash's law. Molar conductivity of any solid is got by the summation of the respective molar conductivities at infinite dilution of its respective ions, each multiplied by the appropriate coefficient, stoichiometric coefficient at a given temperature. So this we are going to calculate for the molar conductivity of calcium hydroxide at infinite dilution, but we get it by getting the molar conductivities at infinite dilution of its respective ions present at a particular temperature. And this is done according to Corash's law in electrochemistry. Say that the molar conductivity at infinite dilution of calcium hydroxide is going to be equal to the molar conductivity of calcium hydroxide. This note here is denoting molar conductivity at infinite dilution. And the difference with this is that here we denoted it with a C. The C just denotes molar conductivity of calcium hydroxide. So I'm saying that where this one with the C is the molar conductivity of calcium hydroxide, and the one with the note is the molar conductivity of calcium hydroxide at infinite dilution. I said that don't worry, we shall look more deep into that in electrochemistry. So molar conductivity of calcium hydroxide, or we get molar conductivity of any solid by getting 1000 times K. And this K must be of a solid divided by concentration. So 1000 multiplied by electric conductivity of calcium hydroxide divided by the concentration. But in chemistry, concentration is also considered to be C, and C is going to be solubility. So in chemistry, in electrochemistry, C can either denote concentration or it can denote solubility, and they all have the same units, which is going to be moles per decimeters cubed. And therefore, making C the subject, you're going to end up with this expression. And therefore, here you have obtained the solubility of calcium hydroxide. Now here, we'll write the expression for the solubility product, or the equation for the solubility of calcium hydroxide in water. So write that solid calcium hydroxide dissolves in aqueous solution to give us its respective ions present in the saturated solution, which is going to be calcium ions and then hydroxide ions. We balance up charges first by putting a 2 here. And then the charges are balanced, also the atoms are balanced. Now here we are saying that here, where the molar concentration of calcium hydroxide is going to be equal to C. Like I told you, C is the same as concentration, and at the same time is the same as solubility. So molar concentration of this is going to be C, which we already got here, up here, moles per decimeters cubed. Now we consider mole ratio to determine the molar concentration of both our hydroxide and our calcium ions. So since mole ratio is 1:1 between calcium hydroxide and calcium ions, we are going to say that molar concentration of calcium hydroxide is going to be equal to the molar concentration of calcium ions, which is equal to C moles per decimeters cubed. And then since the mole ratio between calcium hydroxide and hydroxide ion is going to be 1:2, just like explained earlier, molar concentration of the hydroxide ion is going to be twice the molar concentration of calcium hydroxide, which is going to be equal to 2C moles per decimeters cubed. And therefore the solubility product of calcium hydroxide is going to be denoted by molar concentration of the ions present in calcium hydroxide raised to their appropriate powers. So molar concentration of calcium times molar concentration of hydroxide. Now substituting, you're going to have C times 2C, but this 2C is raised to power 2. And if you open this bracket, this is going to be 4C squared. 4C squared times this C, you're going to end up with 4C cubed. And your units, which I already told you how we get them. So solubility product using conductivity measurements is going to be attained as 4C cubed moles to decimeters power -9. Now we are saying that here, this method can be used for any electrolyte. Just like I told you, this one is non-selective. But the first one is only selective to bases and acids. That means that it must only be for hydroxides. But for conductivity measurements, it's non-selective. It can work on every kind of sparingly soluble salt. And if you want to level up your chemistry, you should only focus at understanding this method. And if you want to understand it the more, make sure that you also understand electrochemistry properly. So you're saying that this method can be used for any electrolyte whose solution cannot be titrated with any suitable reagent, unlike the first one. Factors that are going to be affecting solubility of a sparingly soluble electrolyte. Now here we are going to first look at common ion effect, and we are saying that here, common ion effect. Now notice that this one is very common. It's a very common term that is being asked in each and every chemistry paper that is coming, especially more papers. Now common ion effect, as the name suggests, common ion effect is going to be the precipitation of a sparingly soluble electrolyte from a saturated solution by addition of a solution of a more soluble electrolyte, but this soluble electrolyte being added must be containing one of the ions of the sparingly soluble electrolyte. Now to simplify this is that for common ion effect to take place, we are going to be considering these equations. So for common ion effect to take place, assuming that here I must add a solution which is soluble, assuming I'm adding silver nitrate to this solution. If I add silver nitrate to this solution, silver nitrate is soluble or it's aqueous. Silver nitrate is going to ionize in solution and it's going to add more of the silver ions here. Now these ones are equilibrium reactions. The more silver ions increase, that means that excess of these ones are existing, and we use the knowledge of chemical equilibria to understand this. So if more excess of the concentrations of one of the products is increasing, more of this reacts with the chromate to form back our unionized salt, and that means that we are going to form more of the solid, or we are going to cause more precipitation. And that's what common ion effect means. You're adding another solvent, but the solvent that you're adding is containing one of the ions present in your sparingly soluble salt. So coming up with a definition is going to be the precipitation of a sparingly soluble electrolyte from its saturated solution, simply by addition of a solution of a more soluble electrolyte. But this soluble electrolyte must be containing one of the ions that are contained in your sparingly soluble electrolyte. Now here we are saying that when a solution contains a similar ion is added to a saturated solution of a sparingly soluble electrolyte or salt, the solubility of the electrolyte is going to decrease. Now let's look at the examples and the elaborative explanation of how that happens. So let's say this is under common ion effect, and you will be asked for these terms as quite as often when it comes to the solubility equilibria. So number one, you are going to be considering silver chromate being sparingly soluble in water. That means that this is our sparingly soluble salt. Now explain what will happen to the solubility of silver chromate when each of the following is separately added to it. So Roman number one, when we add silver nitrate. So when you add silver nitrate, what is going to happen? And Roman number two, when you add potassium nitrate. Just like I explained, first of all, you have to first write the equation for the sparingly for silver chromate to be sparingly soluble. And if you do that, you get your sparingly soluble salt, you add it to aqueous solution, and then you're going to get the respective ions, which are going to be silver ions and then the chromate ions. You make sure that you balance the charges first by putting here 2. Now charges are balanced, that means that the whole equation is balanced. Then you also consider, like if you had to answer number 1, we are adding silver nitrate. Silver nitrate is a very soluble salt, so it's aqueous here. So being so soluble, it fully ionizes. So silver nitrate fully ionizes to form silver ions and then nitrate ions. Everything is in aqueous. So what happens? According to this equation, you are seeing that more of the silver ions are going to be existing. So they are going to disturb the equilibrium of the first equation, since we are dealing with a reversible reaction. So more of the silver ions are existing. Once more of them are existing, some of them react with the chromate to form back the equilibrium reverses, or the equilibrium position reverses to the left to keep the value of Ksp constant. Now let's look at the explanations for that. Now the elaborative explanation for that is going to be the following. So for Roman number 1, addition of silver nitrate is going to decrease the solubility of silver chromate, because the silver nitrate added contains silver ions, which are common to the silver ions that are present in silver chromate, and which we already described as common ion effect. Now here, we are going to say that the excess silver ions added are going to combine with chromate ions, just like I earlier explained, in the solution to precipitate the silver chromate in order to restore the equilibrium, maintaining the value of the equilibrium constant, or unchanged, like we looked at this under chemical equilibria. So when you're ionizing silver chromate, we form silver ions and chromate ions. And then, now this is answering Roman number 2. If you look at Roman number 2, we are adding potassium chromate. Now this potassium chromate is containing similar ion of chromate as in our sparing insoluble salt. Now this is going to disturb our equilibrium. So it means that more of this is existing. And once more of this is existing, the concentration of one of our products is going to be increased. And according to chemical equilibria, we say that if any of the concentration is disturbed, especially in the product side, the equilibrium shifts to the left. That means that more of the chromates are going to be reacting with the silver ions to form back our solid, which is precipitation of silver chromate. So also here we are going to be reducing solubility of our silver chromate due to common ion effect. So you are going to be answering number 2 by saying addition of potassium chromate is going to decrease the solubility of silver chromate. And this is because potassium chromate is containing chromate ions, which are common to chromate ions in our sparingly soluble salt, which is silver chromate. Now the excess chromate ions being added, since they're existing in excess in the solution, they are going to combine with the silver ions back, with these ones back to form back the solid silver chromate. That's why you're saying that to precipitate the silver chromate which is present in solution. And they do this in order to restore equilibrium and maintaining the value of equilibrium constant or unchanged. Now let's look at question 2. Question 2, state what would happen if the solubility of calcium phosphate in water when we add sodium phosphate and also when you add calcium nitrate. Now try to imagine this on your own. What will happen if you add sodium phosphate, and what will happen if you add calcium phosphate? Try to imagine it in your head before we proceed the video. So if you look at calcium phosphate, first of all, it's our sparingly soluble solid. So we add aqueous to show that we are dissolving it to get the ions present in the saturated solution. And that's going to be calcium and then the phosphate. We balance charges by putting here 3 and we put here 2. So that balance charges are balanced, and also atoms are obviously going to be balanced. Now the sodium phosphate that we are adding is containing similar ions of phosphate ions, and always what we are adding is a strong electrolyte, so it fully ionizes, forming sodium ions, and then balancing up the charges, we put here 3, and obviously the atoms are also going to be balanced. So the electrolyte we are always adding must always be soluble. It must be soluble, and it should be fully a strong electrolyte, fully ionized. That's why we use a full arrow. But for our sparingly soluble salt, we use a partial arrow, showing that it's a reversible reaction. So here we form sodium ions and phosphate ions. You can see that in these two reactions, we're having phosphate ions in common. That means that we are having a large concentration of phosphate ions in the solution. And this equilibrium is going to be disturbed, and equilibrium is going to shift to the left to keep the value of equilibrium unchanged. But as is shifting to the left, more of the phosphate ions react with more of the calcium ions, forming calcium phosphates, which is a solid, and therefore precipitation is going to take place. Explanation of that, you're going to be saying that here, addition of sodium phosphate is going to decrease the solubility of our sparingly soluble salt, which is calcium phosphate. And the reason is going to be the sodium phosphate that we are adding is containing phosphate ions that are common to phosphate ions present in calcium phosphate. And if that happens, excess of phosphate ions added are going to combine with the calcium ions to precipitate out calcium phosphate, and this is done in order to restore equilibrium and maintain the value of equilibrium constant. So explain number 2, if we add calcium nitrate, if you look at these two equations, we have in calcium ions common in the two, but you ensure that what you're adding is fully ionizing, so that we have excess of calcium ions. So if you have excess of calcium ions, equilibrium is going to shift to the left. So more of calcium ions are going to react with phosphate ions to maintain equilibrium constant. And when they are reacting, they are going to be forming calcium phosphate, which is a solid, reducing the solubility of calcium phosphate, since the backward reaction is one which is being favored. So that's why we are going to say that here, addition of calcium nitrate is going to decrease the solubility of calcium phosphate. And the reason is because calcium nitrate contains calcium ions, and the calcium ions are common to calcium ions present in calcium nitrate. And therefore, the excess calcium ions added are going to combine with the phosphate ions in the solution to precipitate calcium phosphate, and this is done to restore equilibrium and maintain the value of equilibrium constant. Now you're going to be using this one as your revision question. Now let's look at the applications of ionic effect, and this is very examinable in paper 1 chemistry. So ensure that you understand the whole of it. So try out this question. You either reach me out with your solutions, or you reach out to your teacher to guide you on what is supposed to actually be answered. So my number 1, you're going to look at it being applied in the purification of the sodium chloride salt. And sodium chloride is known as the common salt in chemistry. The common salt, since common salt is the same as sodium chloride, we say that here commonly contains quantities of calcium chloride and then magnesium chloride that cause it to be deruxient. So sodium chloride being a sparingly soluble salt, its equation is going to be this, the solubility product equation. Now we are saying that here the sodium chloride is going to be purified by addition of concentrated hydrochloric acid. Now notice that here, if you're adding concentrated hydrochloric acid, since it is a strong acid, it fully ionizes to give hydrogen ions and then chloride ions in solution. Now that means that since chloride ions are existing in HCl that we are adding, and they're also existing in our equation, that means that we are having excess of the chloride ions. So equilibrium of this equation is going to be altered, and the equilibrium position is going to turn to the left. Some of the chloride ions, or the excess chloride ions, are going to react with sodium to precipitate back your sodium chloride, which is the precipitation of the common salt, or purification of the common salt. So that's why we are saying that here, into its saturated solution, which increases concentration of chloride ions in solution, or in the saturated solution. Therefore, the equilibrium is going to be displaced to the left, decreasing the degree of dissociation of sodium chloride, hence precipitating sodium chloride, just like explained earlier on, since the solution is going to be already saturated by sodium chloride. Now, the more sodium chloride precipitates out, the more salt is being formed. Remember that for us to obtain our salt, or to purify our salt, we need precipitates of salt. And that's the purpose of addition of concentrated HCl to common salt or to sodium chloride solution. Now let's look at salting out of the soap. Now during saponification, hot concentrated sodium chloride is going to be added to the mixture so that we can precipitate out our soap. Now during this, we are going to be looking at this under applications of organic chemistry, or we are going to be looking at this under polymerization or saponification. So we are going to be saying that here, soap is a sodium salt of a long chain carboxylic acid, and in saturated solution of soap, it forms soap ionizes according to the following. So its solubility product equation is going to be this plus the sodium ions. R is going to be a long alkyl group chain, and therefore, if you add sodium chloride to this solution, remember that sodium chloride is a strong electrolyte. It fully ionizes to form sodium ions and chloride ions. So there are going to be excess of sodium ions, which are going to react with the carboxylate ions to form back your long chain sodium carboxylate salt, which is a solid, hence precipitating out soap. So addition of sodium chloride to saturated solution of soap increases the concentration of sodium ions, and the excess sodium ions are going to react with the carboxylate ions, precipitating out soap. And that's the function or the applications of common ion effect. We apply common ion effect in two ways. First of all, purification of common salt or sodium chloride, and the other one is going to be salting out or precipitating out of soap. To part B, eliminate this must be part A. So going to part B, we are going to be looking at complex ion formation. Now remember that in common ion effect, the sparingly insoluble salt, its precipitation is increased, hence its solubility is decreased. The more increase its precipitation, the more it decrease its solubility. But here in complex ion formation, it's going to be the opposite. The more we form a complex ion, the more we increase the solubility of our sparingly soluble salt, as we are going to be explaining still according to terms under chemical equilibria. So here we are going to be saying, when a saturated solution of a sparingly soluble salt or a sparingly soluble electrolyte is added to a solution of a soluble salt that forms a complex with the electrolyte, its solubility simply increases. And we are going to look at examples. So example number 1, silver carbonate is sparingly soluble in water. That means that it's going to be our sparingly soluble salt. Now we have to explain what happens to the solubility of the silver carbonate if ammonia solution is added to its saturated solution. Now if you're having silver carbonate, you first write its solubility equation, and the solubility equation for silver carbonate is going to be as follows. Once we dissolve it in solution, we get its ions present in the saturated solution as silver ions and then carbonate ions. After that, we are going to say that addition of ammonia. Now, what happens when adding ammonia is that ammonia comes and reacts with these silver ions. That means that it's going to be decreasing the concentration of silver ions in this equilibrium reaction. And since these are equilibrium reactions due to reversible arrows, once the concentration of silver ions is being reduced, to attain back equilibrium position shifts to the right, and therefore more of the silver carbonate dissociates to form more of the silver ions that are being taken away to restore equilibrium, keeping it constant. So that's why we are going to explain it in terms of such an explanation, and we are going to say that addition of ammonia is going to increase the solubility of silver carbonate, because ammonia solution is going to react with the silver ions, forming a soluble complex of diamine silver ion, and that happens according to the following equation. Whenever explaining something and you give a statement that requires an equation, always write it, because it will increase the marks that you are getting in that particular question. So you're saying that here, once that happens, this is going to reduce the concentration of the silver ions that are present at equilibrium, and therefore more of the silver carbonate is going to dissolve so as to restore the equilibrium by maintaining the value of equilibrium constant unchanged. But notice that here, silver carbonate is dissolving so that to form back the silver ions that have reacted with ammonia. And by dissolving, the more it dissolves, the more solubility, or the more its solubility increases. And therefore, we made the note here that ammonia solution has the same effect on the solubility of sparingly soluble copper and chloride. All that is going to be complex ion formation. So you have to be aware of the complexes that we are having in chemistry, especially those formed with ammonia solution. Number 2, we are going to look at copper 2 iodate is more soluble in ammonia solution than in water. Explain. So the reason for that, copper 2 iodate being sparingly soluble, we first write its solubility equation, and it must be having a reversible arrow. And also this appears to show that you are writing a solubility reaction. Now we are saying that here, addition of ammonia to this is going to increase the solubility of copper 2 iodate. The reason for this, ammonia is going to come and react with these copper 2 ions, forming a complex which is going to be tetraamine copper 2 ion, and it happens according to the following equation. Now, the more it reacts with the present copper 2 ions, it's going to reduce the concentration of copper 2 ions, and this is going to disturb equilibrium. More of the copper 2 iodate has to dissolve to form back the copper 2 ions that have been taken away, so that to retain equilibrium, to keep the value of equilibrium unchanged. So that's why we are saying that here, this lowers the concentration of copper 2 ions, and therefore more of the copper 2 iodate dissolves to restore equilibrium, maintaining the value of the equilibrium constant unchanged, or maintaining the value of equilibrium constant. So number 3, in the same explanation, we are saying that here the solubility of little chloride in cold water decreases on addition of dilute hydrochloric acid, but increases on addition of concentrated hydrochloric acid. Explain. The reason for that is this. The little chloride is sparingly soluble in cold water. Therefore, we write its solubility equation as follows. Now we are saying that here, addition of dilute hydrochloric acid to solution of little chloride is going to decrease its solubility because dilute hydrochloric acid is containing chloride ions. Remember common ion effect. Dilute hydrochloric acid is containing chloride ions that are common to the chloride ions which are present in little chloride. And once that happens, excess of the chloride ions are going to react with excess of these which are formed in solution, react back with lead ions to form back little chloride. And they do that to keep the value of equilibrium unchanged, but also increasing the precipitation of little chloride, hence decreasing its solubility. So the excess chloride ions added combined with the this is not correct. They combine with the lead 2 ions in solution to form or to precipitate out little chloride in order to restore the equilibrium and to keep the value of equilibrium constant unchanged. However, let's look at the point of the addition of concentrated hydrochloric acid. Now we looked at this reaction in group 4 elements. Let's look at the explanation again here in physical chemistry under ionic equilibria. Concentrated hydrochloric acid increases the solubility of little chloride. Reason being, the chloride ions are present in a very high concentration, and therefore, after precipitating out the little chloride, they are going to react with it again. And with reacting with it again, since they are in high concentration, we form what you call a complex. And this complex is going to be tetrachloroprambate 2 ion. Now, formation of a complex is what leads to the decrease of the precipitate of little chloride, hence increasing its solubility, because more of it is going to be reacting with excess chloride ions to form a complex which is soluble, and in turn is going to increase the solubility of little chloride in concentrated hydrochloric acid. So it happens according to the following equation. Now looking at part C, since you have already got the idea, make sure that you explain this on your own. Addition of a soluble compound containing no similar ion as those of the sparingly soluble electrolyte. When a soluble compound with no common ions to a saturated solution of a sparingly soluble electrolyte is added, solubility of the electrolyte increases. Now let's look at the example under this. So example here, we are going to be explaining why calcium methanedioate is less soluble in calcium nitrate but more soluble in dilute hydrochloric acid. Now here we are going to be saying that calcium oxalate is sparingly soluble. Therefore, we are going to write its equation for the KSP equation according to the following represented below. And then hydrochloric acid, remember, it's a strong acid, it fully ionizes. That means that you have to use a full arrow. So beta equations we use half arrows. So we shall form hydrogen ions and chloride ions. To be saying that addition of calcium nitrate is going to decrease the solubility of calcium oxalate. Reason being, calcium ion or calcium nitrate is containing calcium ions, and calcium ions are common to calcium ions that are present in calcium oxalate, and that constitutes therefore what we named as common ion effect. And we say that common ion effect decreases solubility of sparingly soluble compounds by saying that the excess calcium ions therefore are going to combine with oxalate ions in solution to precipitate out our sparingly soluble salt, which is calcium oxalate. And this is done to restore equilibrium and to maintain the value of equilibrium unchanged or constant. And therefore, solubility will be decreased. But however, in presence of dilute hydrochloric acid, the hydrogen ions are going to react with the oxalate ions that are present, that are from our sparingly soluble salts, forming what we call oxalic acid. Now, oxalic acid is soluble. Now, that means that in our equilibrium equation, the concentration of these ones are going to be reduced. Therefore, more of the calcium oxalate dissolves to replace the oxalate ions that are being utilized or that are being neutralized to form oxalic acid. And by doing so, since it's dissolving more to form back this which is being taken away, the solubility is being increased. So hydrogen ions react with oxalate ions forming oxalic acid, and hence more of the calcium oxalate has to dissolve to replace back the taken oxalate ions, and as it dissolves, it is increasing its solubility. That's where we can conclude that this reduces the concentration of oxalate ions in solution, hence more calcium oxalate dissolves to restore the equilibrium and as well to maintain the value of equilibrium constant. Now let's look at the relationship between ionic product, solubility product, and then precipitation. Now if we are to consider this, our electrolyte this as we started with it, we started by saying that Ksp is equal to this. But notice that also ionic product is going to be equal to this. They are the same explanation, they are the same expansions. Ksp is equal to that and the ionic product is equal to this. We are going to be saying that when the ionic product, now notice that here, Ksp is going to be independent. Ionic product is simply this expression here. Product of the molar concentration of the ions present in a saturated solution at a given temperature. Now Ksp, always when you are being told to work out these questions, is going to be defined. Ionic product is the one that you'll be calculating. But Ksp will be given in the question and then they tell you to calculate for, you have to calculate for the ionic product. The way you calculate for ionic product is the same way you calculate for Ksp. But if you come to answering these questions, you are going to find some questions where they tell you to where they give you the Ksp of a given product and then they tell you to calculate for Ksp again. The calculation that you'll be making is going to be for ionic product. So always remember that. Now here we are going to be saying that when the ionic product is less than the given solubility product, more of the sparingly soluble salt dissolves since the solution is going to be unsaturated. So that means that when the ionic product is less than the solubility product, the solute is going to be more soluble. That's the meaning of this statement. If at all you find that after multiplying, the given solubility product in your question is going to be larger as compared to the Ksp that you have calculated, they know that that product is that salt is going to be more soluble in that solution, and hence precipitation is not going to take place. But however, when the ionic product is equal to the solubility product, then no more of the sparingly soluble salt dissolves, since the solution is said to be saturated. So when you have your ionic product being equal to the solubility product, that solution is just said to be saturated. And when the ionic product exceeds the solubility product, that's when precipitation is going to take place. So after comparing the solubility product that you'll be given with in the question with the solubility product that you have calculated, now the solubility product that you have calculated is what we term as the ionic product. So once you see that the ionic product is larger than the given solubility product in the question, then understand that precipitation is going to take place. So precipitation of a sparingly soluble electrolyte is going to occur, and therefore it can be generalized using these expressions. If Ksp is greater than the ionic product, solution is not saturated and therefore no precipitation is going to take place. If solubility product is equal to the ionic product, that means that the solution is saturated and therefore no more salt can dissolve. Now if the solubility product, if the given solubility product in the question is less than the calculated ionic product, or the ionic product is greater than the solubility product, precipitation of the sparingly soluble salt is going to occur. Now this is going to be like the key to gauge you on how you are going to be approaching such questions. So looking at question 1 or example 1, you are being told that when ammonia solution is added to magnesium chloride solution, a white precipitate insoluble in excess is going to be formed. But when the same solution is added to calcium chloride solution, there is no observable change. So you are supposed to explain. Now here we are going to say that magnesium ions are going to react with hydroxide ions to form insoluble magnesium hydroxide. Insoluble magnesium hydroxide formed is basic, and therefore it cannot react with excess sodium hydroxide. We write an equation: magnesium ions reacting with hydroxide ions form magnesium hydroxide. So excess sodium hydroxide cannot react with magnesium hydroxide because it's basic. A base cannot react with a base. And ammonia is a weak base, and therefore it partially ionizes to form very few hydroxide ions. So ammonia partially ionizes in water, just like we looked at it in previous video. It acts as a base. So bases accept protons. And after water donating protons, it forms the hydroxide ion. We use a reversible arrow. Now we are saying that here, the concentration of the hydroxide ions that are found from the weak ammonia base are going to be low for the ionic product of calcium hydroxide to exceed its solubility product, and therefore no precipitation is going to take place. So you find that if we are adding a weak base, we expect a weak base to produce very few hydroxyl ions. In that if you are to get the ionic product, if you are to multiply the molar concentration of the ions in solution, the ionic product is going to be less because the molar concentration of one of the products is very low due to presence of a weak base which gives off very few or a small portion of it. So ammonia being a weak base, it releases a less concentration of hydroxide ions in solution, and therefore the ionic product is going to be less than the solubility product. And he said that once the ionic product is less than the solubility product, there is no precipitation that takes place. So looking at number 2, we are saying that here, when ammonia solution is added to a solution of magnesium sulfate, a white precipitate is going to be formed. However, when ammonia solution is added in presence of ammonium chloride solution, no precipitation occurs. Explain. Now notice that here, ammonia solution being there and ammonium chloride solution being there, we form kind of what you call a buffer solution, and we are going to be explaining in terms of that. So let's start. You're saying that here, ammonia is a weak base, and being a weak base, partially ionizes in water to form ammonium ions and then hydroxyl ions. So ammonium ions formed here the ammonia is a base, so it accepts protons from water, forming ammonium ions, and the water becomes the hydroxide ion. So we shall proceed by saying that the concentration of the hydroxide ions that are found from ammonia is not enough. The concentration is going to be very low for these ionic products. We remember that for any product, we have to multiply the concentration of ammonium ions with the hydroxide ions. So the concentration of hydroxyl ions that are found from ammonia solution is not enough, or is enough to react with magnesium ions for the ionic product of magnesium hydroxide to exceed the solubility product. And once the ionic product exceeds the solubility product, that's when precipitation occurs. And the good thing with these questions, they will tell you that precipitation is occurring or precipitation is not occurring. So what you have to do is you have to explain in terms of ionic products and solubility product. If precipitation occurs, you explain that ionic product is going to be greater than solubility product. If precipitation does not occur, you explain in terms of solubility product being less than the ionic product. So you're saying that therefore magnesium hydroxide is going to be precipitated. So we write an equation of magnesium reacting with the hydroxide ion to form a precipitate of magnesium hydroxide. Ammonium chloride, you are going to be like ammonium chloride is a strong electrolyte, and as we said, every salt is a strong electrolyte, so they completely ionize in solution to form the respective ions. So ammonium chloride completely ionizes, that's why you're using full arrow to form ammonium ions and then the chloride ions. Now we are saying that here the ammonium ions that from the fully ammonium ions from this fully ionized salt are going to suppress the ionization of the ammonia solution, just like we explained in buffer solutions. Because when ammonia solution or ammonia molecules are undergoing ionization, they are forming ammonium ions. And remember that it's an equilibrium reaction. So this salt has already given off one of the products that's being formed. So you find that the suppression or the ionization of ammonia is going to be very limited. Therefore, very few hydroxide ion concentration are going to be produced since its ionization is being suppressed. So that's why we are saying that here the ammonium ions from the salt suppress the ionization of ammonia solution due to common ion effect. And this reduces the concentration of the hydroxide ions that are produced in return. So you find that there are going to be very few, there's going to be a less concentration of the hydroxide ions for the ionic product of magnesium hydroxide to exceed its solubility product, and therefore no precipitation is going to take place because we produced very few hydroxide ions, because the ammonia solution or ammonia molecules were prevented from undergoing ionization by the already present ammonium ions from the fully or completely ionized salt. So number 3, hydrogen sulfide gas is bubbled through a solution of manganese 2 nitrate. No observation occurs in presence of dilute hydrochloric acid, but in presence of ammonia solution, a pink precipitate is formed. Explain. Hydrogen sulfide undergoes partial ionization according to the following equations. Hydrochloric acid undergoes partial ionization according to the following equation. If you look at the two, they are having hydrogen ions present in common. Therefore, we have to explain that. So we are going to say that hydrogen sulfide, being a weak electrolyte, partially ionizes in solution, forming sulfide ions and hydrogen ions. Now, in presence of dilute hydrochloric acid, which is a strong electrolyte, the hydrogen ions, which are present from the completely ionized acid, suppress the ionization of hydrogen sulfide, which is due to common ion effect, because we are seeing here protons, we are also seeing here protons. So due to common ion effect, and this is going to reduce therefore the concentration of the sulfide ions that are formed in return or in solution, and hence the ionic product of manganese 2 sulfide is not going to exceed its solubility product. And once the ionic product is below the solubility product, we say that no precipitation takes place. But in presence of ammonia solution, you are going to find that ammonia solution, being a weak base, is going to produce the hydroxide ions from the ammonia acid. From the ammonia react with the hydrogen ions from the hydrogen sulfide to form water. So ammonia undergoes ionization to form what we call the hydroxide ions, and then ammonium ions, and this is a partial arrow since it's a weak base. Now the hydroxide ions formed react with the hydrogen ions from the acid, forming water, which is a neutralization reaction. Now here we are saying that this is going to reduce the concentration of hydrogen ions present in this solution. Hence, more of the hydrogen sulfide ions, more of the hydrogen sulfide is going to ionize, forming a concentration of sulfide ions high enough for the ionic product of magnesium sulfide to exceed its solubility product. And we say that once the ionic product exceeds the solubility product, always precipitation takes place or occurs. So manganese reacts with the sulfide ions that are being formed to form manganese sulfide, which is a precipitate, at which precipitation takes place. Now here, we are going to look at applications of solubility products as the final part. So we are going to be looking at the sorting out of soap. Solubility product can be applied in sorting out of soap, as we explained before. It can be applied in purification of common salt, as we gave an explanation of it before. We have looked at this to be under what we call common ion effect. And then the other one is precipitation of hydroxides and precipitation of sulfides and precipitation of chlorides, as we have looked at these ones under complex ion formation. So under solubility product, we have learned about common ion effect. You make sure that you are very good at it, definition, and at the terms, and also explaining it. You also have to be good at explaining complex ion formation. And after explaining complex ion formation, you have to also explain the part that you have been doing, whereby we don't form a complex but we present in other elements that react to form different precipitates. That's why we call this one precipitation of hydroxide, precipitation of sulfides, precipitation of chlorides. This video, we meet again in the next video. Now in the next video, we shall be handling calculations that are involved in solubility equilibria purely, so that we can count this done. It's going to be the end of ionic chemistry, such that we go and we start again in organic chemistry. So for those of you having prepared success in your exams,